I'm starting this now, but I'm going to have to break off and do the live chat in a little while's time. So what I want to do now is much briefer than what we had this morning. This is just a very, very quick introduction to some of the ideas of functional programming. So you're familiar with the idea of a subprogram. It's part of a program that does a particular thing. For instance, if I wanted to print out the sum of a set of numbers, I might do something like this. So defining my procedural sum here, give it a list of numbers to work with, and what do we want it to do? We might firstly want to know how long that list is, so let's run the length method on my list of numbers. Then I'm going to set up an accumulator here, so the total starts as 0. Then we're going to do one number at a time for I in range. The length of the list of numbers, and then we're going to do the total is equal to the total plus the current number, which is at position I. This is standard GCSE programming, isn't it? You could do this in Recursive if you really wanted. That looks okay, and then we could just print whatever the total is at this point. Okay, so the runtime connects. That seems to have worked. I can run psum on a list made up of the range 1, 0 up to and including. No, sorry, let's just do this by hand. Psum on the range 1, 2, 3, 4, 5. Close the bracket to pass the parameter there. And we get the answer 15, which is what you get if you add all of those numbers up. That's fine. Okay, this is a procedure. It acts out in the world. It prints something onto the screen there. I'm much more interested in returning this to whatever it was that called this in the first place. In this case, it's going to be just the REPL shell here, the interactive shell, but strictly speaking, we ought to pop that inside a print statement. This returns the total of whatever numbers we pass it, and then prints that returned value up onto the screen here. So let's just reload the function definition now, run that, and lo and behold, we get the number 15 out at the end. The interesting difference here is I can do things with this. So I can take that sum of those numbers and double it. So I've got a number coming back from my user-defined function here, and then I can do something to that number. So we should get the number 30 out of that, and so on. So that's nice. We're able to work with that value. There are lots of things which we could do with. Okay. Typically in functional programming, we try to avoid any of this messiness of creating entities without any good need. There's no real need to create this length variable, to create this total variable. We tend to adopt a more recursive approach to this. So let's have a look at how we would do this in a functional paradigm here. So I'm going to do recursive sum of a list of numbers here now. And the recursive sum of a list of numbers is generally going to be whatever the first number is, so that's numbers in position 0, the initial position, plus, whatever the sum of the rest of it is. So the recursive sum of numbers from 1 up to and including the last, up to the last number in the list there. So just have a look and pause for a moment. So to work out the recursive sum of a set of numbers, we take the initial number, the 1 in my example here, and then we add that to the sum of the rest of the numbers. And that's all we need to do. Well, it's not quite all we need to do, because this won't work. It will look as though it's fine. Look, it's accepted the definition there. I can do print. I don't actually need print because Jupyter here will do that for me. I can do rsum of 1, 2, 3, 4, 5. Sorry, that should be a list I'm passing it. And it's going to crash. I confidently predict this won't work. Oh, in the list index out of range, yeah. So it's tried to keep doing that, but eventually there's nothing left for it to run rsum on. So what you have to do in these recursive definitions of a function is have a base case, the thing where it stops, keep calling itself, and just gives a value back to you. So what we have then is if there are no numbers left, So if the numbers is just an empty list, then the sum of an empty list of numbers is going to be 0. Otherwise, do what we've just done here and take the first number and then add on whatever the recursive sum is of the other numbers in that list. Invalid syntax. You know I keep making that mistake. Double equals in there. Okay, and now our sum should work. It didn't. Okay, what's the problem there? So unsupported operand type for plus, int and non-type. Okay. Else. Oh yeah, I should have returned this. There we go. There we go, and we get the answer 15 back. That's lovely, isn't it? I can, of course, take this a lot further. So, for instance, if I wanted to add up the first 100 numbers here, I would do something like list. Interesting to just try it with the pure iterator. So, from 1 up to but not including 101. I don't think that's going to work. But if I cast the range iterator to a list from that range, I should get an answer out of it. And I'm confidently expecting 5050 as my answer there. That's good. Okay, so we've added up the first 100 integers. How cool is that? I'm going to pause recording now, come back to this in a little while after we've chatted online. Right, so that's just done our live conversation in Collaborate. It was really good to have a few of you there, and I very much encourage anybody watching this to pop in for the 3:31 at the end of the day where we can talk about functional programming. Right, so I've forgotten entirely where I've got to. So yeah, we've got now a recursive definition of adding up numbers. We're able to apply that to a long list. So this is the joy of functional programming, that we can do things with these things rather than expecting the procedure to do all of the work for us. We can abstract that out to a top layer of control. It's also worth saying I could have used psum for this as well. Right, so let's do a couple of slightly more interesting functions than just adding things up. Anybody who's teaching secondary computing at the moment knows that the most important things in the whole world of computer science is being able to convert between binary and denary numbers and back. So let's see if we can get Python to do the work for us. After all, this is the sort of thing which computers ought to be really quite good at. You have got built-in functions in Python for doing binary to decimal conversion and decimal to binary conversion. But we may as well go ahead and build one of these things. So let's have a go at that, shall we? So let's do, I don't know which is the easier way. I think denary to binary is probably easier. Hold on, I've got to deal with this email. Pause. Right, I'm going to turn off notifications so I can concentrate on this now. What were we trying to do? We were going to have a go at, I think it was decimal to binary or denary to binary. So I'm going to create a function d2b, which is going to take a denary number and produce a binary version of that. Now, most of the time, what I want to return here is what I get if let's just think this through. So the first part of it, so what we do is shift right we deal with the first part of the number and then look at the last part of the number. So if it's an odd number, we put a 1 at the end. If it's an even number, we put a 0 at the end, and then we deal with the first part of the number. So what I'm going to do here is return d2b for the first part of the number, which is what I get when I do my arithmetic shift left. So divide everything, floor division, integer division by 2, and then concatenate with, I'm going to take these as strings, what I get by just looking at the remainder on dividing that number by 2. And I can apply that recursively to any denary number, and that should work. Okay, let's pop brackets around the value that we're going to return here. Okay, and then we've got to do the usual recursive thing of just testing whether everything's okay. When we get down to a number 0, then it's easy enough to do. We just return the string 0 at the end there. So if that, else, return t'other one. Okay, so we're going to have to test this because I think that's going to work. Right, let's try that. So what do we get if we do d2b decimal to binary of, I don't know, 42, the answer? I get 0101010. Yeah, that's okay. It's putting in a leading 0, but I can actually live with that. I'm not going to worry too much about that. That's that returning 0. If you don't like the 0 at the start of the number, then just return an empty string there. And then I should get just 101010. There we go. All right, the problem is that now d2b of the number 0, I think, will just give us nothing in return. So swings and roundabouts, we could fix this. I don't know, which do you like of those? I quite like all binary numbers start with a 0 or start with a 1. It's one or the other, isn't it? You can't have it both ways. Probably ought to go with that. Okay, so we've got it going that way. That's looking pretty good. What about the other direction? The other direction, let's define here binary to decimal. And we're going to pass it a binary string this time. And again, the same sort of, what's the general pattern of this? Well, the general pattern for in this direction, binary to decimal, is to take is to look at the last digit of the number, add that on, because that's either going to be a 1 or a 0, and then take the first part of the number, double it as you shift left, and then keep doing that recursively. So we're going to take here int binary of the last digit of the string. We use exactly the same syntax for string indexing as we do for list indexing in Python. So take the last digit there and add on to that. In other words, concatenate. No, add on to this. This is addition this time. Double everything which you get from the first part of the string. So that's binary of everything up to, but not including, yes, the last digit of the string. Of the string. There, that's fine. Pop brackets around that because that seems to help. And that's the general pattern. Again, we've got to do the special case, the edge case. What's the base case for the recursion? So this time, if the string is the empty string, then we're going to return 0 at that point. Else, we're going to return all this. Good. Okay, let's try it in the other direction now. Binary to decimal. What's binary to decimal? Decimal? Binary to decimal. Yeah, okay. For the number 100, we should be getting the answer 4. Yes. Okay, shouldn't sound quite so surprised. Binary to decimal of 101010. And we get the number 42. Binary to decimal of decimal to binary of just any old random number here, 241,212. Convert it to binary, then convert it back to decimal. We get it back. That's such a relief, isn't it? Okay, so that's function and its inverse there. Notice there is no magic trick to calculating the inverse of a function, and there are rules in mathematics which say there's no magic trick to calculating the inverse of a function. That becomes important for cryptographic purposes. Okay, so we've got all of that working now. Where do we go now? Okay, the other tool in your box here is the idea of the anonymous function. That what I've been doing all along here is defining a function to do things. It's possible to define functions in slightly different ways, and we have this idea of the lambda function there. So we can have a different type of function definition here. Double something. What we do with when asked to double something is apply a function to some input and return double that input. Now I'm hoping that this syntax is acceptable to Python. I might have to come back and do an X for this. So take a parameter and multiply it by 2, and that defines a function. Okay, let's have a look what double is. double is a function. So can I apply double to something? Can I apply double to 12? I should get the answer 24 out. Yes, indeed it does. Okay, so I've defined a function in a much more abstract form there, rather than having to go through all of that function definition stuff. That can sometimes come in useful. I can do something like is even as a function. And again, I'm going to do that as a lambda expression, which takes a number and returns whether that number divided by 2 is equal to, sorry, the remainder when taking that number and divided by 2 is equal to 0. Okay, so is even, yeah, should work. Okay, let's try is even applied to the number 12. We should get true back. Ooh, x is not defined. No, of course it isn't, because I changed the parameter of the function there. And that comes back as true, and is even of 13, with a little bit of luck, should come back as... Okay, so we can define functions in that slightly more compact form. I could probably do is odd as equal to lambda, take a parameter, and do not is even of that parameter. And now let's try is odd for 13, should say true. Yes, okay, that's a relief, isn't it? Oh, and I should have put underscores in there rather than attempting to just join the words. Never mind, though. Okay, so we've got lambda expressions or lambda functions, which are these sort of semi-anonymous functions. We've got recursive definitions of functions. This is looking pretty good at the moment. Where do we go next with this? There are 3 higher order functions. The coolest thing about functional programming is that functions are things that we can do things with. We can treat the function itself as a bit of data, as a thing which we can operate with in our programming. And the 3 particular ways we have of doing this is this idea of map and filter and reduce. So map applies a function to everything on a list. And let's do these one at a time. So map is built into Python. So I can take map. Yeah, let's do it this way because you need to see what goes wrong. I can take my decimal to binary function and apply that to the first, oh, I don't know, like 15, 16 numbers. So apply that to a list made up of the range of numbers up to but not including 16. This won't work. It will return a map object. Okay, so it's a map object stored at some memory location. But this is an iterable thing. I can convert that into a list by just popping list to and fro. This is much more elegant in true functional programming languages. You do this in Haskell, and it looks beautiful as code, whereas this looks a little bit clunky. Python isn't really a true functional programming language. But there we go. So, you know, that exercise you do about can you count in binary up to 15, there we can prove that a computer can do that. Notice there's no repetition involved in this. This is not iterating over a list. Well, it is iterating over a list, but it isn't a for next loop or a for in range loop. All of that is dealt with by mapping this function to the object, by passing a whole list of things into this function. So map is itself a function whose first parameter is a function. So it's what we call a higher order function. One of its arguments is a function. If you preferred the stuff which started with a 0 there, then I can change my definition here. And then when I map that, I'll get the leading zeros out of all. Whether you prefer one or the other, I don't mind, you know. Okay, so that's map. The next one we're going to do is filter. So again, let's get it wrong first. So I'm going to filter this time. And what I want to do is take my function is odd and apply that to my list, the list of the numbers from 0 up to but not from 0 up to but not including 16. Okay, so filter according to the rule whether they're odd or not. The numbers 0 up to but not including 16. And we get a filter object. Again, this is an iterable thing. So, oopsie daisy. So I can apply a list to that. 1, 2, 4. Close the other bracket. And we get those numbers. I can again apply a map object to that list of odd numbers in there. So I can do exactly what we've done before. I can list what you get when you apply the map of denary to binary onto this list that I've just constructed. And you do this a lot in functional programming, this idea of making functions from other functions or applying functions to other functions. So this takes the numbers 1 to 16, it filters them so we've only got the odd numbers, and then it converts all of those to binary. And you should see that the binary values of all of the odd numbers end in 1. If not, we have gone wrong somewhere. Look, they all end in a 1. Isn't that cool? There are probably other things which we could have done with that if we'd wanted to. Okay, and the last of this big family of higher order functions is this idea of reduce, which is where we apply an operation to every item on the list. So very often in GCSE programming, you've got to sort of work out the total of a list of numbers there. So how would you do that in a functional paradigm? Well, we'd use this higher order function called reduce. Now, unlike filter and map, that's not built into base Python. They managed to persuade Guido that map and filter were really very useful functions. He was not persuaded that reduce was necessary. So that's in an external library or a standard library, so called functools. Functional tools. I'm going to import the reduce function. Okay, that seems to have worked. Right, okay, so what are we going to do here? We're going to reduce using addition. So I'm again going to create a function which just adds things together. Oh, look, we get the little helpful hint coming out. Okay, and that's pretty much exactly what I'm going to do here, isn't it? So let's apply reduce using a lambda function. We could just go and define the function as we did earlier, but I can do this using a lambda expression. So lambda, which takes two parameters, x and y, and adds them together. In other words, a function that does addition. You could probably click, in other languages, you can create something just raw out of the addition operator. But in Python, we've got to sort of go through this slightly more tortuous process. So I'm going to apply that particular accumulator function, addition, to the numbers in a list. So we're going to take the list of the range of the numbers 1 to, oh, we did up to, sorry, 1 up to, but not including 101 earlier. And that should give us what we had started with, which was my recursive or procedural sum. So add up the numbers from 1 up to, but not including 101, and tell us what the answer is there. And we should get the answer 5050. And indeed we do. Isn't that reassuring? Okay. We can, of course, this list just needs to be an iterable object. So as before, what I can do here is take this list of all of the odd numbers up to but not including 16 and apply my addition function to that list. So what do you get if you add up all of these numbers? Well, curiously enough, you'll get the number 64. Isn't that weird? And if I took up to but not including 20, I'd get 100 out of this. If I took the number 100 here, I'd get, well, what's half of 100? That's 50. 50 times 50, 2,500. Hey, there's something really weird going on. It's like halve it and then square the answer you get. There's a shortcut method there if we were looking for one. I think that's, oh yes, one last thing. So we've got this idea of the factorial expression. What do you get if you multiply a dry cough, not yet persistent? If you multiply all the numbers up to but not include up to and including something, we call that factorial. So factorial 4 is 1 times 2 times 3 times 4, which is 24. We can do exactly the same thing with reduce. It's not just for adding things together. So x star y sorry, we take a function which takes two numbers and returns the product of those numbers, and then we apply that to the range I said up to but not including, I said 1 to 4, so up to but not including 5, and I've got to convert that back to a list before I can apply the function to it. Syntax. Oh, because it starts at 0, and 0 times anything is 0. There you go, there's your 24, and factorial up to 10, all of the numbers from 1 up to but not including 11, multiply them together. You get a huge number. What is that? 3,628,800. We can do all of that, in one line of code, whereas the usual GCSE method, I don't know, like 6 or 7, possibly less than that. Right, so that's enough from me by way of introduction to functional programming. What I'd very much encourage you to do is play around with this and then have a go at some of the Project Euler problems, trying to adopt a functional paradigm for these. But I'll put that into when I get the slide deck together. Stop the recording.